live class we will discuss the material which is shared in the Google Classroom. So first topic is the epoxidation and the Sharpless Asymmetric Epoxidation. In the Google Classroom we have already discussed about the matter in detail, but still I think you need the mechanism as well as the whole chemistry of this epoxidation as well as the Sharpless epoxidation through this technique. So first start with the simple epoxidation of the alkene. Generally, the epoxidation procedure, it is the electrophilic addition, and in this case the epoxidation generally takes place for the alkene, and you know alkene having the pi electron cloud, so it is generally electron rich center or the electron rich species. So in epoxidation, you can see generally oxygen in presence of silver and strong heat, it is used to carry forward the reaction and it will generate the epoxide. But in these cases you need the metallic silver which have the toxicity. Not only that, you have the higher temperature, so that's why the reaction condition is very much drastic and the yield of the product of this reaction will be less. So how you will get rid of from this discrepancy? In this case generally you can see for the epoxidizing agent, you know the reagent, that is the peroxy acid or peroxybenzoic acid. So the peroxy acid means this is the functional group, that is the peroxy acid, that means the peroxo bond is present there, and this acid or this species acts as an epoxidizing agent. In this case this oxygen is electrophilic in nature. So if there will be some electron rich species, they will attack this electron deficient oxygen. Now there are several examples for the epoxidation. One is the trifluoroperoxytic acid or peroxy acid. Another reagent is the peroxybenzoic acid, and the most used reagent, that is the MCPBA. This is the metachloroperoxybenzoic acid. You know the structure. Generally nowadays MCPBA is used for the epoxidation. So this is the per acid or peroxy acid. With respect to this acid group, this is the meta position, so this is metachloroperoxybenzoic acid. Someone is not be muted, please be mute everyone, there is some noise. Okay, someone is online, please be mute. After this discussion you can ask the question. Now please be mute, otherwise there will be a noise. Okay, so now how the reaction mechanism proceed in this epoxidation state. So if we take a general alkene, say this is the CH2CH2, this is the simple alkene, the epoxidation takes place of the alkene bond, and here we are using the MCPBA. MCPBA, you will get the epoxide. So the reaction mechanism, basically the reaction mechanism will be same for the all epoxidation step in presence of the MCPBA. So we can write the MCPBA like this way. Say this is the peroxo bond in this MCPBA, and I mentioned that this is electrophilic in nature. So the rest of residue, sorry, This is the aromatic one. I can consider this is the aromatic one. This is the metachlorobenzene group and double bond O. So this is the MCPB where AR equals to this one. So now in this case, our target is to shift or add this oxygen in this electron rich system. So that means if this is the electrophilic oxygen, then we can show the charge distribution like this way. So this is the minus and this is the plus, if we think like this way. So that means it will attack here. Now we know all the center here octet rule is maintained. So when it will donate its electron here, now the octet will be violated. So the oxygen will try to retain its octet. So how it will possible? Then when it will donate the electron here, simultaneously this bond will be broken. That means this electron is now located at this center, if I think like this way, and this is the plus. Then it is now electron deficient. So after this electron localization, it will be added here. So that means as a whole we can show this electron will be donated here, simultaneously this bond will be broken and that electron will be donated at this center. And not only that, when this will be the mechanism, then this proton will be abstracted by this pi cloud. That means we can show this is the plus, this is the minus. So that means there is the attack by the oxygen. So when there is the plus charge, again there is the electron deficiency. So this electron deficiency will be met up by breaking of this bond. So we can write it minus. Now as a whole you can see the total molecule is now the charge balance. Okay. So in this case we can show the mechanism in a concerted pathway, that is so this is the alkene, this is the peroxybenzoic acid or the MCPBA. So in this case this will attack here, simultaneously this bond will be broken and it will donate the electron here. It will abstract the hydrogen and simultaneously this bond will be broken to make up the electron density of this bond. So as a whole, if I draw the transition state in the epoxidation step, you can see there is a partial bond formation, the bond formation in between the carbon and oxygen. Again there is a bond formation between the carbon and oxygen. So that means the formation of the epoxide bond. Similarly there is the bond, breaking of oxygen-oxygen, that means the peroxy bond. Formation of the carbon-oxygen double bond, breaking of the carbon-oxygen double bond, and formation of the oxygen-hydrogen single bond. So as a whole we can show the transition state like this way. Say this is the breaking of carbon-carbon single bond. Now here is the formation of the carbon-oxygen single bond. Here again the formation of the carbon-oxygen single bond. So that is the epoxide bond. Similarly this bond will be broken. Here is the formation of the new bond, carbon-oxygen double bond. This carbon-oxygen double bond will be now broken. So simultaneously there will be the formation of the oxygen-hydrogen single bond and there will be the breaking of oxygen-hydrogen single bond in the peroxybenzoic acid. So as a whole, this is the transition state of the epoxidation, simple epoxidation in presence of the peroxybenzoic acid or MCPBA or CF3COOH. So you can see here this is the 5-membered cyclic transition state and 3-membered cyclic transition state. So it is proceed via cyclic transition state, and you know that the formation of the cyclic transition state is energetically stable. So this is the mechanistic pathway, and finally the product you will get from here, that means formation of the epoxide bond plus this is double bond O, AR, OH. So this is your side product, and This is the general mechanism of the epoxidation. Now, in the study material, you can see that we have performed the epoxidation in the cyclohexene system. So, cyclohexene system, if it is the unsubstituted cyclohexene system, that means the pure cyclohexene, then the epoxidation mechanism, that means the epoxidation pathway, this mechanism will be the same. And basically, we will get the structure. So, this is the cyclohexene. Upon epoxidation by using the simple MCPBA, we will get the structure, this one. That means we can show it either the top of the plane of this whiteboard, or you can write it bottom of the plane of the whiteboard. Both are identical. Both are identical because there is no chiral center is present in the cyclohexene ring, and you know cyclohexene is achiral in nature because there is a plane of symmetry. Now, in case of cyclohexene, there will be some different approach by attacking of this MCPB. So, before starting with the epoxidation of the cyclohexene, let us focus on the conformation of the cyclohexene. Generally, we know the conformation of the cyclohexane. This is the cyclohexane. All the carbon is sp3 hybridized. And you know that cyclohexane has the stable conformation in the chair form. So, this is the chair conformation of the cyclohexane. And not only that, in this case, you know cyclohexane generally contains two types of bond. One is the axial bond, another one is the equatorial bond. So, generally in cyclohexane, if I draw the bonds, first I am drawing the axial bond. Here you can see that this 1, 2, 3 bond is upward side with respect to the cyclohexane ring, and this 1, 2, 3 bond is downward with respect to the cyclohexane ring. So, this upward face or the top face of the cyclohexane or any system is generally named as the beta face, the top face, and the bottom face or the below face or lower face is generally named as the alpha face. So, now which bond is axial? In cyclohexane system, the bond which is perpendicular with respect to this framework, and the bond is just anti-parallel with respect to the other bond, that is designated here the axial bond. So, you can see here basically 1, 2, 3, these 3 bond is perpendicular with respect to this framework, and they are oriented in a parallel direction. They are parallelly oriented. Similarly, the other 3 bond, they are oriented towards the downward, and they are also perpendicular with respect to this framework, and not only that, they are parallel as well as in the downward phase. And if you can see that if I consider this is the axial bond with respect to this position, the adjacent position, this is the anti-parallel. Simultaneously, this bond is also anti-parallel. So, this is another axial bond. So, simultaneously, this is other axial bond, this is axial, axial, axial. So, if these are the axial, then the rest of thing, the rest of the bonds, here you can see, now these two bonds are not anti-parallel with each other. Here the bond is basically anti-parallel with this cyclohexane system or the carbon-carbon bond. So, this is the equatorial bond. and here you can see this is anti-parallel with respect to this carbon-carbon single bond. So this is the equatorial, this is equatorial, equatorial. So all these bonds are the equatorial bonds. So generally a pure cyclohexane ring contains 6 axial hydrogen and 6 equatorial hydrogen. Okay, so this is the general conformation at a glance for the cyclohexane. Now in case of cyclohexene, here you can see in case of cyclohexene, now there is additional double bond is present. That means this is sp2 hybridized, this is sp2 hybridized. You know the geometry of the sp2 hybridization is planar, and here you can see both the sp3 as well as sp2 present. So that means planar geometry as well as the non-planar geometry, both are present. So in cyclohexane ring you can see the whole molecule is a non-planar, so the whole system is non-planar. So if I put some double bond here, the non-planarity will be lost. That means some kind of strain is applied in this chair conformation. So for the cyclohexene type of system, to release this strain, the stable conformation is the half chair conformation for the cyclohexene. For the cyclohexene, the stable conformation is the half chair. Now how you will draw the half chair? Say in this case, say if I do the numbering 1, 2, 3, 4, 5, 6. So first we will draw the double bond, then add a point here and here and connect with them. So now as per numbering, this is 1, 2, or you can write this is 1, 2, 3 whatsoever, 1, 2, 3. Now our next target is to draw the other two carbon. So in half chair, generally you know this is the half chair conformation. So similarly we will draw here. So put another carbon atom here and this is here, and now connect these two and these two, and finally draw like this. So as a whole you can see this double bond is towards your side, that means towards the viewer, and this bond is away from the viewer. That's why there is a breaking of the bond to draw the half chair of the system. So the numbering is 1, 2, 3, 4, 5, 6. So that is maintained here. So this is the stable conformation for the cyclohexane. Now cyclohexene. Now in case of cyclohexene, you know that for the cyclohexane there is the two type of bonds. One is the axial and another one is the equatorial. So similarly here you will get axial as well as equatorial bond. Fine. But additionally the other two bonds, two type of bonds you will find in the cyclohexene type of system. So basically if I draw the cyclohexane, you can see, say if I consider this is the hill, so this is the hill and this is the valley, so this is the valley. Here you can see this is the axial bond, so I will draw, this is the axial bond perpendicular to this framework, and you as a convention is same, this is the beta phase, that is the top phase is the beta phase and the bottom phase is the alpha phase. So this is the top position or the beta position. Similarly the other bond, axial bond, is at this position. So this is another axial bond at the valley. Okay, now this is the equatorial bond at this position. So this is the equatorial bond, and this is the another equatorial bond. So another equatorial bond is there. So this is pure axial, pure equatorial, this is pure equatorial, pure axial. Now this position, we are not bothered about this position because this is sp2 hybridized, it is a planar system. So no assignment of the axial as well as the equatorial with respect to these two sp2 hybridized carbon containing hydrogen. So we will not consider this. Now the rest of two position, this two position is important. Here you can see I will draw the bond like this way. Now this 2 bond is neither pure axial bond not pure equatorial bond, but you have to maintain the convention. So that's why they are named, they are written just like pseudo axial bond and pseudo equatorial bond, or by symbolizing psi a prime and psi e prime. So now which bond will be the pseudo axial and which bond will be the pseudo equatorial? In the cyclohexane, if you look at the structure of the cyclohexane, I am draw the heel like this way. Now the adjacent carbon is this one. So here this is the axial bond, the equatorial bond in cyclohexane. And as you know that the axial bond is anti-periplanar with respect to the adjacent axial bond. That means if this is the beta phase, the other axial will be in the alpha phase. So same convention we will maintain here, but just change the name. So if this is the axial bond at the beta phase, this is the alpha phase, this will be the pseudo axial. So this will be the pseudo equatorial. Now in this case, this is the axial bond at the alpha phase. So the other axial bond should be in the beta phase. This is the top phase or beta phase. So this should be the pseudo axial and this should be the pseudo equatorial. So as a whole, this is the general conformation of the pure cyclohexane. Okay. Now for the epoxidation of the alkene, cyclohexane, so if this is the cyclohexane, pure cyclohexane, and you are using the MCPBA, the mechanism will be the same. So aromatic double bond O, this is the mechanism, the general mechanism of the epoxidation. So the transition state will be like this way, that means partial breaking of the double bond, formation of the epoxide bond, and the rest of thing will be same. So this is the transition state, 5 plus 3 member cyclic transition state, and as a whole you will get the structure. That means I am not drawing the side product. So now here you can see both the phase having same type of steric environment. That means here 2 hydrogen and here also 2 hydrogen. No other steric repulsion or the steric, no difference in the steric factor. So that means both the phase are equally probable. That means epoxidation can be facilitated from the top phase and it can be also facilitated from the bottom phase. We can draw the structure like this way also. Both the structure is identical, so equally you will get the product. But if there is the substitution in the cyclohexene system, then what will be the scenario? So there are two common examples. One is the OH containing, another one is the OSE containing. Look at the position of the substituents. This means the OH is the top of the whiteboard or towards the viewer or the beta phase. Both are same meaning. And you can see this center is chiral. If I apply the 4b plus rule, this is 1, this is 2, this is 3, anti-clockwise rotation. For this anti-clockwise rotation you will get the minus, and this is the fourth group. We know the 4b plus, So combination of this, that is the minus, so configuration will be the S. So that means this center is chiral. Similarly, we will get the configuration of this center is chiral. So that means this is the chiral center. You know, if the chiral center is present in the non-planar system or additional chiral center is present in the system, they have the influence in their chiral induction. So that means now both the face of this cyclohexene ring is no longer same, they are now diastereotopic in nature, because this is the additional chiral center in the cyclohexene system. So in this case, if we add the MCPBA, you will get, this is the product, exclusively this one, not the epoxide bond at the downward position. And similarly, in this case, if you add the MCPBA, you will get this is the the epoxide bond at the downward position. So now what is the reason behind these two different scenarios? Here we have to consider the two factors, that is the electronic factor as well as the steric factor. You know, in between the electronic factor and the steric factor, electronic factor having always higher influence over the steric factor. So, and the electronic factor, generally you know resonance is the one of the predominant electronic factor, hyperconjugation electronic factor. Not only that, if there is some interaction like dipole-dipole interaction or say hydrogen bonding interaction is present in the system, then that will facilitate over the steric factor. So now for this type of example, so this is the cyclohexene system where additional OH group is present. So first we will draw the cyclohexene ring, pure cyclohexene ring in their actual conformation. This numbering is not the IUPAC numbering. Okay, so in this case we will draw it so this is the pure cyclohexene. So 1 2 3 4 5 6. Now I am starting numbering from here. So 1 2 3 4 5 6. In this case we mainly consider these two positions. Here you can see that the OH group at the beta phase or top of the phase. So this is the top phase or the beta phase. So OH reside at the third position. Now this is the OH group, and this position, you know, if this is the axial hydrogen, this is the equatorial one, so this is the pseudo axial position. So OH group will reside at this position. Now how it will influence the MCPBA? So in this case you can see it is hydrogen is present here. Okay, now though the OH group is sterically bulky, more bulkier than the hydrogen, but due to this interaction, that means the intermolecular formation of the intermolecular hydrogen bonding with the MCPBA, the epoxidizing agent is bound to attack from the top phase. How? Here you can see, if this is the MCPBA, now I am drawing the transition state. Here you can see that this is the breaking of bond, formation of the epoxide bond. So in this case you can see in the transition state it is stabilized via the formation of the intermolecular hydrogen bonding here, and I am drawing the rest of the structure. So this is the scenario. Here you can see additional intermolecular hydrogen bonding present. So that will facilitate the MCPBA to attack exclusively from the top side. So that means the OH, if the OH reside at the top side, the MCPBA will attack from the top side. If it is in the bottom, the MCPBA will attack from the bottom side. Due to this presence of the additional intermolecular hydrogen bonding in the transition state, it can stabilizes the molecule or the system. So that means the direction of the attacking species is dependent on the position of this OH group. So as a whole, you will get the structure like this. That means the epoxide bond is at the same position of the OH group, or we can write okay. So this is the influence of the electronic factor, that is the hydrogen bonding. Now what will be the scenario for the OSE group? In case of OSE group, you can see AC means that is the acetyl group, OCO CH3, that is the OSE group. So there is hydrogen present which is attached with this electronegative oxygen. That means no questions of the intermolecular hydrogen bonding formation in the transition state. So that means electronic factor is absent. So if electronic factor is absent, then we will consider the steric factor. So again we will draw the structure of the cyclohexene. So this is the cyclohexene, and similarly the OSE will be at the top face according to this configuration. Now here you can see, if I write it, say O, if this is the scenario, here you can see no questions of the hydrogen bonding, but this sterically bulky group is present at the top position. So that means this is the double bond, this is your electron rich position, it will interact with the epoxidizing agent. So if the top phase is sterically blocked, then that means the beta phase is actually inaccessible. So the MCPBA is bound to attack from the bottom phase to avoid the steric repulsion. So MCPBA is bound to attack from the bottom phase to avoid steric repulsion. That means in this case the transition state will be just inverse. So that means the simple mechanism, no questions of the formation of the intermolecular hydrogen bonding. So as a whole, you can see now this epoxide is located at the opposite position with respect to the OSE. So our product will be this is our product. That means we can write OSE, if it is the top position, then the epoxide bond will be at the bottom position. So these are the two important parameters which can guide the epoxidation state, and this reaction is basically one of the example of the diastereoselectivity, because both the isomers you will get here, this is the OSE and another one is the OH, both the isomers they are diastereomers, and here you will get the diastereoselectivity. So if there is any problem, like say you want to synthesize this epoxide and this epoxide. Here you can see both are the same side, and here you can see both are in the opposite side. So basically this is the pathway how you can show the step. Simple. Here you will use the OH, then MCPBA. You will get your target product, that means the epoxide at the top position with respect to the OH group. But if you want to form this epoxide, next step, so here you have to first protect this group. So how you can protect it? If you use TMSCl, that means trimethyl silyl chloride. If you use TMSCl in presence of mild base, say pyridine or triethylamine, it will be directly converted to the OTMS. So OTMS means OSI, 3-methyl group is attached here. So that means hydrogen is absent. No questions of the formation of the intermolecular hydrogen bonding in the transition step. So if it is absent,
राइट साइड में नहीं दिख सर,
नहीं दिखाई दे रहा है, रुको,
सर राइट साइड, हाँ हाँ सर,
ठीक है अभी,
और थोड़ा सर,
ठीक है,
हाँ सर ठीक,
So in this case, this is the silyl product. So here hydrogen, no questions of the intermolecular hydrogen bonding because hydrogen is absent, and not only that, this is the sterically bulky group. So same thing will be, it will be similar like in presence of the OAC. That means this is now the sterically crowded group. So if you add the MCPBA to minimize the steric crowdance, OTMS, this will be the structure. And now in the final step, the deprotection of the TMS group, if we use TBAF, tetrabutyl ammonium fluoride. Generally fluoride has the higher affinity towards the silicon. Tetrabutyl ammonium fluoride, that is the deprotecting agent of the TMS group. So it will be converted to this epoxide. So that is the utility of the reaction. Okay. So this is the epoxidation pathway. Now there is another important topic, that is the Sharpless asymmetric epoxidation. Generally, the Sharpless asymmetric epoxidation is used for the epoxidation of the allyl alcohol. You know, this is the allyl carbocation. If we add the OH here, so this is the allyl bond, and this is as a whole named as the allyl alcohol. So in Sharpless epoxidation, we will epoxidize this substrate, and in this case, in the study material you have seen there are lots of reagent is used, but one important reagent is the chiral reagent. That means the presence of the diethyl tartrate or diisopropyl tartrate. Okay. So basically these are the esters of the tartaric acid, and the reagent other is used, that is the titanium tetraisopropoxide, This is the catalyst. The tertiary butyl hydroperoxide, this is acts as an epoxidizing agent. Next, 2 angstrom molecular sieve. This is used to accelerate the reaction. Dichloromethane, that is the DCM, used as solvent, and the reaction temperature is 10 degrees Celsius or 20 degree, minus 10 degree or minus 20 degrees Celsius. It is fixed for all the reaction conditions. But only important thing in this case is the presence of the chiral reagent, that is the date or DIPT. As these are the chiral molecules, so it has the optical activity or the optical rotation. Generally we know the optical rotation may be plus or minus. Similarly, plus, minus. In this case, we will apply some tricks that how can you predict the product easily by without doing any mechanism, because you can see the mechanism and it is very much complicated. This is processed through via the 18 electron rule, the coordination chemistry and whatsoever. I am not discussing about the mechanism, but how you can predict the product by using this method. So in this case, you have to consider two important parameters. One parameter is the orientation of the allyl alcohol, and another thing, excuse me, and another thing is the the optical rotation of the chiral reagent. That means, is it plus or minus date or DIPT? So now in this case, say I am starting with this example. So this is your allyl alcohol, and here if you use the all the reagent, that means titanium isopropoxide, tertiary butyl hydroperoxide, molecular sieve, DCM minus 10 degree Celsius. Now if you use plus date, you will get one isomer, and if you use minus date, you will get another isomer. So that will control the formation of the product. How? If you use the plus date, here you will get this, but if you use the minus date, you will get the epoxide at the beta position. Say if you use the minus date, you will get this epoxide. Now how you will predict that which epoxide bond will be beta and which epoxide bond will be the alpha in allyl alcohol? So here the orientation of this double bond is important. You can see if this is the allyl alcohol, and we can consider this bond or this is in the plane of the whiteboard. So now if I do the numbering, say 1, 2, now I can show the bond like this way, say 1, 2. Now with respect to this double bond, this is your right hand side and this is your left hand side. Now here you can see this is the bond, and I am rotating this bond like this way. That means it is not vertical, but if I rotate it like vertically, then you can see it will be rotated like this way. And similarly, this will be the bond, because here you can see this is the right hand position, this is the left hand position. So OH. Now the orientation we will mention here. You can see that the allyl bond is in the downward position, or the OH containing bond is in the downward position. That means this is the upper position of the double bond and this is the lower position of the double bond. Now these are the four direction, and how you will mention it. You can see this allyl bond is in the lower right position. So this is the lower right orientation. Similarly, we can show the structure in another approach like this way. Now I am rotating the bond anti-clockwise. Here I am rotating the bond in the clockwise fashion. Now I am rotating the bond in the anti-clockwise fashion. So if it is anti-clockwise, then one will be in the down. I am rotating like this way. One will be the down, two will be in the top. And you can see if this is in the top, this bond will be rotated. So OH. Now this is your right hand side, this is your left hand side. Here you can see that the allyl bond is attached at the upper position of the double bond. So here we will mention it as the upper left orientation. So if the allyl bond, both this position or the orientation is equivalent, basically you can show either in the lower right position depending upon the position of the allyl bond, or you can show it in the upper left position. So if the orientation is lower right or upper left, then by using minus date or minus DIPT, you will get the beta epoxide. This is fixed. And similarly, if you use the plus date or plus DIPT, you will get the alpha epoxide. So this is the thumb rule here, that is the tricks in this the process, that if the orientation of the allylic double bond is in the lower right or upper left position, then by using minus date or minus optically active chiral agent, you will get the beta epoxide, and if you use the plus date or plus optically active chiral reagent, you will get the beta epoxide. And similarly, the scenario will be just opposite with respect to the other two orientation, like this way. Say here if I do the numbering 1, 2, first I can rotate it clockwise to make the bond vertical. So 1, 2. If it is 1, 2, you can see if I rotate this, so this bond will be rotated at the left hand side. Now the position, this is the right hand side, this is the left hand side, upper, lower, 4 direction is here, and you can see the allylic bond is attached at the lower position of the double bond, and it is in the left hand side. So this orientation is lower left. Or similarly, another approach, if I rotate in the anti-clockwise fashion, here the rotation is just in the opposite direction, anti-clockwise fashion. That means now 2 is up, 1 is down. So this bond will be like this way. So with respect to this double bond, right hand side, left hand side, upper, lower. Now here you can see this is upper right. So when the allyl alcohol achieves this orientation by using minus date or minus DIPT, you will get the alpha epoxide, just opposite scenario of the previous one. And if you use the plus date, you will get the beta epoxide. So whatever will be the example, your target is to find out or to isolate the allylic double bond, then find what is the rotation or optical activity of the Chiral reagent, and accordingly find predict your product. So just another last example for this asymmetric epoxidation. A typical example, like say if this is the phenyl, this is the OH, and this is say ethyl. Now in this case, as a whole, it is a molecule, and here you can see that the allylic double bond is present or allylic alcohol is present. So we can consider this is the derivative of the allyl alcohol. So our target is, or our objective is to consider only this position. We will forget about the others. So here you can see, if I do the numbering, say 1, 2. Now in this case, our target is to rotate this double bond vertically. So any of the orientation you can show, you need not to show the both orientation, lower right, upper left, or vice versa. So here I am considering, or that is I am rotating the bond anti-clockwise fashion. So that means now this is the double bond from here to the vertical position, and say this is 1, this is 2. Now in this case, only you have to look at this bond. So this is at the right hand side position. Okay, this is the OH, and this is the phenyl ring, and this is the ethyl. You have to maintain the trans fashion here, and I have maintained here. Now you can see that this allylic bond is in the, say this is the right hand side of the double bond, left hand side, upper, lower. Here you can see that the allylic bond is in the lower position of the double bond, and it is in the right hand side. So this orientation is the lower right. Lower right orientation is here, and say your target is to form so this is your target. You want to form the epoxide at the beta position. So lower right orientation, you have to use either minus date or minus DIPT. So what will be the summary for the asymmetric epoxidation, Sharpless asymmetric epoxidation? That means lower right or upper left. If you use minus date or DIPT, you will get beta epoxide. If you use plus date, you will get alpha epoxide. And similarly, if the orientation, this is the allylic alcohol orientation. If the orientation is just reverse, that means the lower left or upper right, then by using the same reagent, that means minus date you will get the alpha epoxide, and if you use the plus date, you will get beta epoxide. Okay, so that's all from the Sharpless asymmetric epoxidation. That means as the epoxidation of the double bond in different systems.